In this video, we solve problem 9.3.039, Part A, from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to use a graphing utility to find the indicated partial sum S sub n and complete the table. Then we're asked to use a graphing utility to graph the first 10 terms of the sequence of partial sums. Then it says for each series, that's the series in Part A and the series in Part B, compare the rate at which the sequence of partial sums approaches the sum of the series. Now we're not going to do this because we're not doing Part B until another video. In this video, we're just going to focus on Part A. The video for Part B is already online on the Calculus 2 Homework Help playlist. So let's look at this first series. We see that it's a geometric series because we have this constant times a constant raised to the n minus 1. Every time we go from term to term, we're multiplying by another 1/9. So that makes it a geometric series. It turns out that that will converge to this 63/8. That's the first term of the series, which happens to be 7, divided by 1 minus the common ratio, which is 1/9. 7 divided by the quantity 1 minus 1/9 turns out to be 63/8. And I've added the decimal approximation 7.875 right here. Now I didn't write it down here, but in the problem statement on WebAssign, it asks you to round these partial sums to 4 decimal places. So my plan for this video is first to show you what a partial sum is, just to refresh your memory a little bit. And then we're going to use a calculator online to compute these partial sums for large n. We're going to do n equals 5 by hand, and then we'll use a calculator for n equals 10, n equals 20, n equals 50, and n equals 100. And then we will use a different calculator, one actually created by a different instructor on Desmos.com, to graph the first 10 terms of the sequence of partial sums. Now, I will include links to the partial sum calculator that we used for this in the description of this video, and I'll also include a link for the Desmos calculator. I think the Desmos calculator is a really wonderful calculator for showing you both the terms of the series and the partial sums of that series. So let's just review briefly what a partial sum is. So this is a series because we go from n equals 1 to infinity, and we're told to add up terms that have this form. This sigma means add, and it's saying to go from n equals 1 to infinity. So we're going to add up infinitely many terms. This tells you where to start counting. So we'll plug in n equals 1 here. That will give us 7 times 1/9 raised to the 1 minus 1. 1 minus 1 is, of course, 0. And any number other than 0 raised to the 0 power is 1. That's just going to be 7 times 1, which is 7. That's our n equals 1 term, and then this says add. So you want to substitute in n equals 2. You let the index increase by 1, and you evaluate that expression at n equals 2. And of course, 2 minus 1 is just 1. So this is 7 times 1/9. So we're going to get 7/9 there. And then we substitute in n equals 3. So we have 7 times 1/9 raised to the 3 minus 1. This is 7 times 1/9 squared, or 7/81. And you keep going like this. I'm going to go up to n equals 5 because we need that for our nth partial sum here. So we'll substitute in n equals 4, and we'll substitute in n equals 5. And then I'm going to add little dots at the end to indicate that this continues in this way forever, because we're going from n equals 1 to infinity. This is going to be 7 times 1/9 cubed. That's what we get when n equals 4. And then when n equals 5, we have 7 times 1/9 raised to the 4th power. And that turns out to be 7 divided by 729. And this one turns out to be 7 divided by 6,561. Now, if you're thinking, how did you do that? It's because I've actually already done the arithmetic. I did that on my calculator before. So we've got this, and that's our series. And the claim is that if you have a geometric series and you're multiplying by a fraction, a number between -1 and 1, a proper fraction, as you go from term to term, then it turns out that you're adding something that's so small that the sum converges to a finite number. And in this case, that finite number is 63/8. And if you're saying to yourself, what do you mean the sum converges? Well, that's where the partial sums come in, because we say that this infinite series converges, this sum of infinitely many terms converges to some number if the sequence of partial sums converges to that number. And the sequence of partial sums is just the sum of the first n terms. So S sub n, well, if we're thinking of this as a sub n, this is going to be a sub 1 plus a sub 2 plus a sub 3, and then you stop when you get to the nth term. That's a sub n. So in our case, this is a sub 1, this is a sub 2, this is a sub 3, this is a sub 4, and this is a sub 5. So if I wanted to, I could write out the first partial sum. That's just a sub 1. In this case, it's 7. The second partial sum is the sum of a sub 1 and a sub 2. So it's 7 plus 7/9, whatever that is. Of course, you could get a common denominator and figure that out. S sub 3 is a sub 1 plus a sub 2 plus a sub 3. So we'll have the 7 plus 7/9 plus the 7/81. S sub 4 is the sum of the first 4 terms. Hopefully you get the idea. Oops, I guess I don't need that because the first one's a 7. And we were asked for S sub 5 here. They say when n equals 5, find the fifth partial sum. And that's just the sum of the first 5 terms. So we want 7 plus 7/9 plus 7/81 plus 7/729 divided by, or plus, excuse me, plus 7 divided by 6,600 or 561. So that is our fifth partial sum, and that is the number that we want here. And we're asked to round that to 4 decimal places. But I think I would like to show you the other partial sums as well first. So our first partial sum is just 7. And then if we add the first 2 terms, we have 7 plus 7/9. Using my calculator for that, that's 70 divided by 9. And the decimal approximation of that is 7.7 repeating. Actually, that's an exact answer. And then here, we want to take that last answer and we want to add 7 divided by 81. And that gives us 637/81, which is approximately 7.8642 if I round to 4 decimal places. Then if I want the next one, I take the third partial sum. This is S sub 3. That's what I just calculated. And then I add the 7/729. And the exact answer there turned out to be 5,740 divided by 729, which is approximately 7.8738. And then the last one, for going up to S sub 5 is this plus the last answer plus this last term. And the reason I can do that is because all I'm doing is I'm taking the last partial sum and I'm adding one more term to it, because we had A or A1, and then we had A1 plus A2, and then A1 plus A2 plus A3. So I'm just taking the last answer and I'm tacking on that last one. That's what I'm doing in my calculator. So I've got this, and my calculator did not even give me an exact answer this time. But I want it to round to 4 decimal places. That's going to be 7.8749 approximately to 4 decimal places. Okay, so that's the answer that they want right here. Now, it is tedious to write these terms out for n equals 10, n equals 20, n equals 50, and n equals 100. Nobody wants to write out 100 terms and then type all of those little fractions into your calculator. If you understand the idea, then you can use these calculators appropriately. So what I will do is I will show you how to, or I will show you a particular online calculator that I like to use to compute these. But you want to remember what these represent. This is the sum of the first 5 terms. A sub 1 through A sub 5. We're adding these guys together. This is going to be the sum of the first 10 terms. So A sub 1 through A sub 10. So the A's, those are the terms of the series. They keep getting smaller, but the sum of the series is getting larger because we just keep taking the last number and adding one more to it. So we're going from 7 to 7.7 repeating. And then we've got this number, which is approximately this number. Then we have this number, which is approximately this number, and so on. And we're asking ourselves, does this partial sum approach a finite value? It's 7.7 repeating, 7.8642, and so on. And it turns out that it does, because it's a geometric series, and it turns out that it converges to the number 63/8, or 7.875. That's what we mean when we say that this series converges to this number, is that this sequence of partial sums, these values on this list, 7, 7.78, 7.86, 7.87, 7.875, 449, and so on, they're getting closer and closer to 7.875. So now I'll show you my online calculator for this. It's actually not mine, it's just a resource that I found online somewhere. Now, this resource was actually pretty easy to find. All I did was go to Google. Actually, I didn't use Google, I used DuckDuckGo. I went to DuckDuckGo and searched for partial sum calculator. And this is one of the first ones on the list. And this is giving you automatically the sum of 1 over 3 to the n, as n goes from 1 to infinity. We don't want that. We want the sum of 7 times 1 over 9 raised to the n minus 1 power. Now, we know that the sum of the series is 63/8. That was given to us. We could also have calculated that ourselves. It's going to be the first term, which is 7, divided by 1 minus the common ratio, which is 1/9. If we do all that arithmetic, we get 63/8. Let's see if that's what they give us. So click calculate. Infinitely many terms. We're going from 1 to infinity. Yep, and that's exactly what they get, 63/8. Now, for partial sums, we don't want to go from 1 to infinity. We just want to go from 1 to some particular value. So the first one was for n equals 1 through 5. They say add up the first 5 terms. So I changed the n value to 5, click calculate. And see, they've expanded it for us. They've written it in the reverse order, but that's exactly what we have on this paper here. We have 7 and 7/9 and 7/81 and 7/29 and 7/6,561. And it's all written out, and then they're adding those together. And then when you get, when you do that calculation, you get the exact answer of 51,667 over 6,561. Now that is approximately this number. and they round out to many more decimal places than we need. We only want to go out to the 4th decimal place. So that's 7.8749. And that was the answer that we got when we did this by hand and we used our handheld calculator. And you might be saying, okay, how do you do that for n equals 10? It would have been tedious to do it on our paper for n equals 10, but we'll use this calculator instead. So start at n equals 1, and we're starting with n equals 1 because that is what this says right here. This tells us to start with n equals 1, and then we want to go to 10. Click calculate. And we see the exact answer. Is it that huge integer over that huge integer? Excuse me. And then they give us a decimal approximation. That's approximately 7.87499999. There's a lot of nines there, but we want to round to the 4th decimal place. Since there is a 9 behind that 9, we've got to round up sort of twice. So we're going to round to 7.8750 for n equals 10. Now, I didn't expand it this time, but they did it for us. This is a sub 1 plus a sub 2 plus a sub 3. This one here is a sub 4. That's a sub 5. That's a sub 6, a sub 7, a sub 8, a sub 9, and a sub 10. So the fractions, the a's, the values of the 7/1/9 raised to the n minus 1, those are getting smaller and smaller, but we're adding more and more terms together. So we're taking these values and the fractions are getting smaller and smaller, and then we add them, and it turns out that we get this number over here. And that's approximately equal to this. But this is the sum of the first 10 terms, and they've expanded it for us. And we see that we get approximately 7.8750, which is actually the exact answer that we're looking for. Now, the 10th partial sum is not actually the exact answer, but after going up to n equals 10, when we're rounding out to 4 decimal places, we actually get the exact answer after rounding. So I bet we're going to get the same exact answer after rounding for n equals 20, because it's just going to get closer and closer to that value. The partial sums are, excuse me. And so this is the sum of the first 20 terms. They've expanded the 20 terms for you. There's your exact answer. And we see that that is approximately 7.8750 again. Let's do the same thing for n equals 50. And they've already rounded for us to 7.8750. And then we want to do the same for n equals 100. So the first 100 terms. Now, eventually the calculator just stops expanding for you because they don't even want to write out the 100 terms here. But if we were to write out all 100 terms and then add those 100 terms together, this would actually be the exact answer. And there's not even enough room on the screen. Like you have to sort of like highlight and scroll to see the entire integer in the numerator and the entire integer in the denominator. But it's approximately 7.875. And we want to round out to 4 decimal places. Okay, so that is how we complete that table. Again, I'm going to put a link to that partial sum calculator in the description of this video. Now then it says use a graphing utility to graph the first 10 terms of the sequence of partial sums. Well, that means I want to graph S sub 1, S sub 2, S sub 3, S sub 4, S sub 5, and then I need S sub 6, S sub 7, S sub 8, S sub 9, and S sub 10, which of course I could find using that calculator again, but there's actually a better calculator. Someone else used Desmos to create a partial sum calculator. So we're going to use that one to do this second part where we're asked to graph the first 10 terms of the sequence of partial sums. So again, what we're graphing here is n equals 1 and s sub 1, n equals 2 and s sub 2, oops, n equals 3 and s sub 3. Eventually you want to get to n equals 10 and s sub 10. That's our goal. We just want to graph those 10 points and then see what they look like. Now we know that when n equals 1, s sub 1 is 7. So we should see something that looks like this. When n equals 1, s sub 1 is 7. When n equals 2, this is obviously not to scale. S sub 2 is 7.78 approximately. And so on. When n equals 3, we get 7.8642. And they keep going. But we're going to have 10 points there on our scatter plot. It's going to be a scatter plot for those first 10 partial sums. Okay, so this is the calculator that I'm going to take you to, that I'm going to link in the comments. Now, this is not the right function. Our function is, or our nth term of our infinite series is 7 times 1/9 raised to the n minus 1. They have 3 times 1/2 raised to the x minus 1. So we need to change this function. So I'm going to take that and I'm going to make it a 1/9. I'm going to take that and I'm going to make it a 7. And the blue curve is the function, the exponential function, it's decreasing, that comes from just the nth term of this series. But I don't want to graph that blue curve. We can just click this little I guess, icon over here and it's gone. But then what they're doing is they're saying, okay, plug in x equals 1, 2, 3, 4, and so on. I like to use the variable n for series. So let's use an n here. And then rather than calling that x sub 1, let's call it n sub 1. And hopefully now you see two things. So this f of n sub 1 is the nth term of the series. So it says when n equals 1, f sub 1, so that's the nth term, or normally we would call it a of n, actually a sub n. Maybe let's call it that. Change our labels a little bit. I wonder if it would let us do a subscript. No, it won't. Okay, sorry, I'm going to go back to the notation that they were using before. There we go. So we'll call this a sub, or a of n is this. And then we've got our n1 here, a of n1, and the sum as j goes from 1 through n1 of a of j, or I prefer I. Labels really don't matter. But okay, so these are the nth terms of our series. So when n equals 1, if we plug in n equals 1 to this, we get 7 times 1/9 to the 0, so we get 7. So that's this orange point right here. If we plug in n equals 2, we have 7 times 1/9 to the 2 minus 1. 2 minus 1 is 1. So this is 7 times 1/9, so it's 7 over 9, which is this 0.7 repeating. That's right there. And that point is plotted there. If n is equal to 3, this exponent becomes a 2. So we end up with 7 times 1/9 squared. So that's 7 times 1 over 81, or 7 over 81. And that's approximately equal to this value. And that's that point there. So we see the sequence, the nth term is getting closer and closer to 0 when we're this orange scatter plot down here. Those represent the first 12 terms of the sequence a sub n. Actually, it's going up to the 14th term of the sequence a sub n. But we don't want the sequence a sub n, we want the sequence of partial sums. So we don't want just these numbers on the list graphed. That's what we have with the orange plot here. We want this, that's s sub 1, and then this plus this, that's s sub 2, and then this plus this plus this, that's s sub 3, or this plus this plus this plus this, that's s sub 4, or this plus this plus this plus this plus this, that's s sub 5. We want all of those. And that is represented by this expression over here. The sum as I goes from 1 through n of the a sub n's, or as of the a sub i's, excuse me. And we're just using a different letter as our index because we want n to be the top number up here. So we're saying, just give me the first term, the sum of the first 2 terms, the sum of the first 3 terms, the sum of the first 4 terms. Those are the black dots on this graph. So if you don't want to see the graph of a sub n itself, just click on this little orange scatter plot icon. I'll call it an icon, and now it's gone. And then you can see that this is what the graph should look like. Now, we were asked to graph this for the first 10 terms, so I actually don't need this guy, or this guy, or this guy. We just want the first 10. Well, that's what our graph looks like for the first 10 terms. Okay, so you can go to this calculator and modify it the way I have. You had to change the function, maybe get rid of the orange scatter plot. After you change the function, the black graph is the scatter plot for the partial sums. That's the 7, and that's the 7 plus 7 over 9, which is approximately 7, well, that's exactly 7.7 repeating. And then this one is 7 plus 7 over 9 plus 7 over 81, which is this number, which is approximately 7.8642, which is right there. And then we take all of that and we add 7 over 729. So it's this plus this plus this plus this. And that gives us this fraction, which is approximately 7.8738. That's the 4th partial sum. So that's the 4th little point on this graph. And we've done that for n equals 1 through 10. And those sums are being graphed right here. This plus, or that's our first partial sum, second partial sum, third partial sum, fourth partial sum, fifth partial sum, and then so on. We continue for n equals 6 through n equals 10. So let's go to WebAssign and look at the options. So here are our options for part A. You can tell that the answer is supposed to be this one, but let's say you didn't see that. Okay, first of all, I can just use process of elimination to decide which of these is the graph of my sequence of partial sums. We know that the partial sums are approaching 7.875 or 63 over 8. So the second one can't be it, because notice that the y values for these points are all above 8. Here's y equals 8, and those are all above the horizontal line y equals 8. So it can't be that one. These y values are all between 1 and 4, or actually it looks like between 1 and 3. Those are not it. These y values are between 1 and 2, so that's not it. We want y values that are getting closer to 7.7 or 7.875. And we know that when n equals 1, we have 7. This has got to be it. When n equals 1, there's the point y equals 7. When n equals 2, y is 7.7 repeating. It's really close to 8, but at least it looks like it's less than 8. When n equals 3, we get approximately 7.8642. It looks like it's at 8 again, but it's not. It's just a little bit less than that. This is the only one that's even close to the numbers on this list. Not the numbers on this list, which go out to n equals 100, but the numbers on this list that go from n equals 1 through 5. So we would choose this one because by process of elimination, it can't be this one. The y values are too large. It can't be this one or this one because the y values are too small. These are the only y values that match the y values for our sequence of partial sums for this particular series. Now in part B, you do exactly the same thing. Again, I will link the Desmos sequence of partial sums calculator in the description, and I will link this partial sum calculator in the description of this video as well.